Hey, how's everybody doing? Everybody's muted now. Well, this is an interactive, participant-driven meetup, so please feel free to unmute, to chime in, say hi, any of that good stuff. Let me smooth that. I'm on Slack as well if anyone wants to reach out there, and I'm also monitoring the Zoom chat window, so feel free to shout out there. I am seeing a bunch of new names today, and also not a lot of familiar names. So I hope everyone will kind of chime in and say hi. Here's the kind of general agenda for this session. So we'll start with a community discussion in a couple of minutes. As I mentioned, this part is definitely participant driven, so you'll need to unmute and kind of chime in. That takes us about, we'll spend about 10 minutes on that, and then I'll be turning the reins over to Mark for his presentation. His presentation will be about 45 minutes. I haven't changed it. I always forget to change the slide. Usually folks are free to ask questions during the presentation, and they don't need to be held to the end. Mark, do you have any preference on how that goes?
Sorry, I had to unmute. No, great. Just whenever you guys want.
Okay, so feel free to chime in with questions as Mark is presenting, and I'll be monitoring the Zoom chat and can kind of open up the mic for anyone who wants to speak. A few words on upcoming meetups. So we've been running 2 meetups a month nowadays, and a quote-unquote Americas meetup is really just a scheduling issue. This one is evenings in the middle of the month, and the quote-unquote EMEA meetup is for those of us in North America, midday, late morning to midday, but evenings in Europe. In addition to that, we've got 2 study groups going. Both are working on different courses offered by Fast AI or Fast.ai. There's a deep learning study group, which has been going on for a few weeks, but is going to kind of restart tomorrow in conjunction with the launch of the Fast AI, the latest version of their course, which starts on Monday, and a machine learning study group, which is based on the on-demand course. It's their new machine learning course. The deep learning course focuses on, well, deep learning, the machine learning course focuses on like decision trees and random forests and things like that. Of course, we're always looking for presenters. If you're interested in presenting a paper, it doesn't need to be one that you've written, just one that you're excited about presenting. You can visit twimlai.com/meetupcfp and express your interest there. So now is the community discussion, and to kind of get us started, I've got a couple of prompts up here. Certainly fair game is questions or comments on recent podcasts, TWiML AI podcasts. But we'd also love to hear from you on any topics or guests that you'd like to hear about or hear from, projects that you're working on or things that have caught your interest out in the news, new papers, projects that you've seen from others, and just in general, anything that has caught your interest about machine learning and AI since last time. And so this is where I open it up to you. I've got some prompts here just in case. Anyone see this MIT $1 billion commitment to kind of reshaping itself around around AI. It just came out, yeah. It looks like they're kind of cutting across all of the departments in the university and kind of trying to integrate AI into a pretty wide variety of disciplines. Any thoughts on that one? Or any other, any takers to jump in and share something with us?
Well, I guess that they want to do a big step ahead of Carnegie Mellon and Berkeley and Stanford and the other big universities there.
I haven't, I know Carnegie Mellon is very well invested in the space and has done quite a bit in terms of partnerships with folks. I think they've got stuff going on with Google and Uber. MIT already has a research partnership with IBM and probably several others. So it'd be interesting to see if this is something that spreads to a lot of other universities. These kind of industrial, or I guess this isn't necessarily a industry academic partnership, but those have been getting pretty popular in the AI space of late. Anybody see the NVIDIA Rapid announcement? Anyone take a look at that? That one is this one. I saw it, but I have not taken a look at it in a lot of detail, but it looks like kind of a machine learning platform with kind of baked in support for GPUs. I'm not sure what, at that level of like description, I'm not sure what is necessarily new about that, but they do talk about being able to use algorithms like XGBoost and others using GPUs as opposed to being just limited to like deep learning algorithms. It's been a while since you guys have made it so hard for me. Mahesh, you've got to have something.
Yes, good morning, good evening to all of you. I saw the MIT announcement. I think it is absolutely required, given the spate of news of China taking a lead in AI.
Yeah.
And I have started preparing for my November presentation. So I just went through the papers and I realized there are many more out there, who done a lot of good work in entity embeddings. On a work front, I've been very busy because this is the month where we have to file our tax returns, so we've been all busy with that.
Wow.
Yeah.
Are you using deep learning for that?
No, I wish I could. I probably will in sometime in the future, not now. not deep learning, maybe machine learning.
Maybe machine learning. So Mahesh is going to be presenting in November on entity embeddings. If any of you were part of our first run through of the deep learning, the fast AI deep learning course, one of the big things that I think a lot of us didn't really expect to see and left a big impression was the section on the course that talked about entity embeddings, which, not to steal Mahesh's thunder for next month, but it's basically a way to apply machine learning to problems that have traditionally been the domain of kind of tabular analytics. So analytics on numerical data, not videos or audio or things like that we associate deep learning with. And Mahesh, since then, I see it all over the place. Like in interviews, I'll be talking to folks and they'll explain, things that they're working on. And, one of the very first questions that comes to my mind all the time is, oh, are you using embeddings for that? Could you use embeddings for that? And there are just a ton of applications for it, just both kind of traditional embeddings as well as entity embeddings as were discussed in the course.
Yes, there was a very detailed Twitter article which came out last month. I don't know whether you saw that. It was only on embeddings. I'll post the Twitter, yeah, embeddings at Twitter. And I think there was a talk also given at one of the O'Reilly conferences in I think California last month on the same topic. So that's the one, the first link that you get.
Yeah.
In fact, they talk of an embedding store that they have within Twitter.
Oh, really?
Yeah, so they essentially create these embeddings, and they have a feature store in which other users can use these embeddings in their own machine learning problems. And they talk of both static embeddings as well as dynamic embeddings. So they are really, I think they are the first major player to really talk about what they are doing. Besides, some of the Google papers keep referring to them on and off, but I thought this was the first major effort which has been published in this area.
Right. Well, of course, there's the Pinterest pin embeddings blog post and the Instacart, like the shopping embedding ones that I know you're familiar with. But this is an interesting one, and I don't think I've come across anyone talk about dynamic embeddings previously.
Yes. And even the interview you did with on the Open Dota,
Yeah.
project. So I found a link yesterday which also talks about their embeddings in very, very much detail, as detailed as this article. I'll just put it up on the Slack right away. So as we had mentioned in the talk in July, a lot of companies are doing it, and it's good that people are talking about it right away. Yes, that's it. That's the one.
I don't think I'd seen this one either. This looks really interesting. Nice. So you're going to talk about all of this stuff next month?
No, what I'm trying to do is, since the focus is on embeddings, the 3 papers that you referred to, I'm trying to look at what is similar and what is different as far as the use of embeddings across those 3 papers is concerned. And try and look at some generic learnings, because which can be used by people within their own organization, because I think that's most relevant. That the takeaway should be to be use something as much as possible.
Okay. Question from Whitley Yee. Would this include embeddings for things such as ICD-10 diagnosis codes? I don't know what ICD-10 diagnosis codes are.
Hey everyone, I'm Whitley. So I'm very new to this, or kind of new to AI. I'm currently a second-year resident right now, and so a lot of my interest kind of falls into a lot of like healthcare applications. And so I've been looking into some papers and talking about like for prediction, instead of using like the actual, so like ICD-10 codes are how everything is diagnosed and billed in the medical world, and so that's kind of what the EHR is filled with, like electronic medical record. And so some papers were talking about like kind of comparing whether you actually just use the actual code itself versus create like an embedding, and then compare like how close they are to each other in the embedding. And so I was interested in kind of whether that had a lot of improvement in models in healthcare if you used embeddings versus like our traditional way of coding, because at least in healthcare, codes get really confusing because all the models I've read about, or like all the AI models, all use ICD-9 codes. And so everything incorporated that, but then the government shifted and everybody moved to ICD-10 codes. And so now like no old models would, I guess, technically work on any of our current data, because we all have new codes now.
It sounds like folks are exploring the use of embeddings for this. Basically, what the embedding stuff allows you to do is to kind of project these codes into some space that has, you know, where the different codes have semantic relationship with one another, and use them, use kind of that semantic relationship to explore the differences between these codes, or to relate codes, or like cluster codes, things like that. But Mahesh will be talking a ton more about embeddings next month. But it does sound like, you know, not having seen any of the papers you're referencing, it does sound like folks are looking at embeddings for these codes. Cool. Well, it's a quarter after, and it's time to turn things over to Mark. So I'm going to stop the share on my end and welcome Mark, and thank you for joining us to talk about active learning from data. And you're still on mute. There you go. You're unmuted.
Oh, thank you. Okay, you beat me to the punch here. We're going to be talking about a paper called Active Learning from Data. This paper was based on, or this presentation is going to be based upon a paper by Ksenia Konyushkova. Did I get that right, Sam? Raphael Schnitzman and Pascal Foix. I first heard about this paper through a previous interview that Sam gave to Ksenia, and it really grabbed my attention because active learning is so important in some of the things that I do. And I'm going to kind of just go through both a particular domain example to put things to give things more a context. Okay, then we're going to go through some simple active learning mechanisms, and then we're going to go into what the paper discusses. The example that I'm going to use is a text classification example. And I'm going to just switch to Access for a second. I have a database here of 54,000 records that represent equipment defects and equipment and what fixes were applied to that equipment. But because I want to save my job, I coded them up for this presentation into just a series of made-up tokens. But the concept is that in this particular text classification example, given the text of the defect, I want to predict a code that is going to be 0 or 1. The 0 code is going to mean, yeah, this really does sound like it's a defect, and the 1 code says, you know, it's a complaint, but it's not a defect. So going back to the presentation, an example would be that the defect would begin by saying, my car didn't start. And a mechanic went in and said, oh, gee, we have to replace the starter. That's going to be counted as a defect. But if it was, gee, I heard this loud noise when I went over a bump, and it was discovered to be some package that was in my trunk, that's not a defect. So the idea is to take these 54,000 records and classify them as to whether it's a defect or not. And what we would really like to do is to build a machine learning algorithm to automatically classify these records. And of course, a machine learning algorithm needs training data. If I was to gather experts in a particular equipment being maintained, then these experts would have to go and label defect or not a defect on thousands of records. In real life, it turns out that the experts will also have to categorize the data in 3 or 4 different ways. And I've seen them take about 500 records per day, which means that to classify all 54,000 records would take about 108 staff days, which is a lot of time. So the goal is to classify, in some sense, as few records as possible. Let's say 5,000 records. Train a machine learning algorithm, and then have that algorithm classify the other 54,000 records automatically with high accuracy. And the central question we're going to ask here is, how do we select the records to manually label to minimize the number of records reviewed while achieving high accuracy? So the idea is that we want to reduce as much as possible the manual time and let the machine learning do as much work as possible. At this point, I'm going to switch to a notebook to give you more background. What I'll be showing in the notebook is a typical text classification machine learning algorithm. We're going to use a bag of words. We're going to use what's known as the term frequency, interest document frequency scoring. We're not going to show you a lot of the pre-processing of the text that was done prior to setting up that access database. I'm not going to show you the stop words or how I process abbreviations and things like that. So at this point, we're going to hop into a Jupyter notebook. And I've actually run everything. I'll be happy to rerun things again, but the very first cell here are just the imports. And we're importing in a vectorizer from sklearn. We're importing in a classifier, in this case, a linear support vector classifier. The next thing that we're going to do is to import in the data into a pandas data frame. So we did these with these few lines of code, and when I look at the first 5 records, we see that we have the E code. The E code is what we're trying to that's the label. It's what we want to predict. And the various text. Again, the text has been coded in a weird way so that you don't actually get to see the true domain. So, as I said, the typical method for text classification is a bag of word tricks that ignores the order of the words. There's other classification techniques that care about the order of the words, and you can also expand just the bag of words to use what's known as 2 grams or 3 grams, which would be pairs of words strung together, or I could use LSTMs. But bag of words seems to do a pretty good job. I should mention that we've done a lot of work and experiments with n-grams, with embeddings, and LSTMs, and we keep going back to the more simple ways of doing it here. So what I have here is that I've read in the data.
Say, Mark?
Yes?
Can I ask about that? Is it just the complexity of those other techniques doesn't justify the incremental performance, or is there some other factor?
Actually, what we found is, I mean, there's a couple more tricks that I typically throw in here, but what we found is that it doesn't actually improve, that we're not getting better accuracy. And we've thrown a lot of technology.
Okay.
The way is just doing quite well.
Okay.
Can
I ask if anyone else has any other questions for Mark before we jump back in? Either via the chat or unmute. All right, go ahead. Thanks, Mark.
Sure. Typically what you do is that you create a vectorizer, which then takes the defect data and transforms it and comes out with a very large sparse vector of terms. So what we've done is that we've taken the input data. This is just a column of text, okay? Not the E codes, not what I'm trying to predict. And we make it into an array that has 54,000 rows by 3,000 columns. And these would be 3,000 of the most important tokens, most important words that the vectorizer finds. And I also just count how many category 1s, those are the records that we deem are not defects, and there's about 16,000 of them, and how many category 0s. This is an unbalanced problem here. It's not greatly unbalanced. It's not like a credit score in which you have less than 1% being rejected and the other greater than 99%, but it's still an unbalanced categorization. To give you a feel of what the vectorization does, is that the very first 2 rows of X, now this is in sparse format here, says in row 0, words whose index is 119, 649, and so on, get various scores. The bigger these scores, the more important that word is according to the TF-IDF scoring. And then I also have row 2 here, which has, in fact, more words. Even though I say that usually a good choice is a linear support vector machine for classification, this was actually the result of extensive study. And if I wanted to do a tenfold cross validation to obtain what would be the accuracy score if I used all 54,000 records, I come out with a tenfold cross validation score of about 0.94. Just not bad. Actually, the clients tend to be happy with even 0.8. So 0.94 is good. But for the purposes of this talk, let's pretend that we only had 2,000 records that are labeled, and that the other 52,000 records are not. Okay, so if we only had 2,000 records, how well are we going to predict the other 52,000? And I did a very function in machine learning. I am splitting up my data into a training set and a test set, and the test size is going to be 54,000 minus 2,000, or about 52,000, 51,932 to be exact. And I come up with 2,000 records now in my training and 52,000 records in my test set. I then go and I create a little function that is going to fit this according to the linear support vector classifier, predict, and then score, and come out with both the score and confusion matrix. And what I find out is that the accuracy is about 0.91. Okay, so using only 2,000 records and not the entire 54,000 records for training, the accuracy goes down. It goes down quite a bit, 0.94 to 0.91. So the next question is, and this is kind of what the active learning is about, is that suppose that we go and we ask the experts to code up another 999 records. Now, we chose 999 and not 1,000 records because I didn't want to confuse the number of rows with the number of columns. So this way, I get a training set with 2,999 rows and 3,000 columns. And the first thing to do is, what would occur if we were to just choose records randomly? Okay, just choose these 999 records randomly. Well, I skipped over a step, which I'll just point back to. That after I had read in the defects, I shuffled them. I just randomly reorganized them. So, I'm sorry, I have to scroll down. So, what I'm going to do is I built a little function that says, if I have indexed these in my test data set, okay, I want to shift those records from my test data set to my data set. And I use this function which I define of here, I'm not going to actually go into how that function works. I'm taking advantage of the fact that the vectorizer stores things in a row-wise sparse matrix format. So after I shift these records in, and I put them into new variables, I see that my training set now has 2,999 records as expected. The original 2,000 and the 999 kind of randomly chosen records. My test set has 999 less records than before. And what I notice is that my accuracy went up from 0.907 to 0.917. It went up one entire percentage point, which is pretty good. But is there a better way? And I'm going to explain what is the most common way that people do active learning, and that's to develop an uncertainty score. Okay, an uncertainty score says when my machine learning algorithm tries to classify a record, how certain are we of that record? And the trick is that we can have our classifier come out with, I hate to call them probabilities. It's they're really scores. They're not true mathematical probabilities, but everybody else calls them that, so I'll call them probabilities. They come out with a probability of does this test record should I classify it as a 0 or as a 1? Recall that if I want to classify myself, or if I want to classify a record as a defect, I'm giving it a label of 0. If I wanted to classify a record as not a defect, I'm giving it a label of 1. So I use a hidden method of support vector classifiers to come up with a list of probabilities. And if I print that out, the first 10 rows of the X test set, which is when I applied my my classification to the records in my test set, looks something like this. And I'll just go through one example here. It says that the support vector classifier gave a score of almost 0.75 to classifying it as a 0, and it gave a score of almost 0.25 of classifying it as a 1. Typically, if I do just a pure prediction from the support vectors, it would give me back a prediction of label 0, because this score was higher than this score. In this record here, the normal prediction would give me a prediction of 1, because the probability score that it was a 1 was 0.61, which is greater than the probability score of of when it was a 0. Now I'm going to develop my own uncertainty score based upon these probabilities, and it's going to be basically, I'm going to subtract these two probabilities from each other, take the absolute value. So when I subtract off 0.75 from minus 0.5, I'm going to get a score of 0.5. Okay, so my uncertainty score that I'm going to use is strictly this. Other people have typically used an entropy score. Because this is a binary classification, an entropy score and my simple uncertainty score are more or less the track along the same way. A very low uncertainty score, okay, says that I am very uncertain, okay, that my algorithm, that my machine learning algorithm is having a really hard time picking whether I should label it as a 0 or a 1. And I'm not confident about those. So if I went and sorted all these uncertainty scores and print out what the first 10 are, I get the first 10 have very, very low scores. It says that there was some record in which the machine learning algorithm really couldn't tell the difference whether it was a 0, a label 0, or a label 1.
Mark?
Yes?
I just wonder if that shouldn't be called a certainty score rather than an uncertainty score, if a low score means it's more uncertain.
You know, you're completely right. The reason why I use uncertainty score, I probably should have subtracted 1, was that the literature uses the terms uncertainty score, okay?
Okay.
But you're out, you caught me. And of the 999 records with the lowest ones, the 10 largest, the 10 most certain ones, have scores of about 0.025. So it kind of said that it gave a score to one label of what, 0.48 something, and gave, no, 0.49, and gave a score of about 0.51 to the other label. So even at the 999th most uncertain one, it's pretty uncertain. But if I take them and I just use those 999 records and I shift them from my test set to my training set, and then I run the algorithm, the machine learning algorithm on that, I get an improvement, 0.92. That is certainly better than my randomness, okay, of 0.917. And if I, just for laughs, said, well, yeah, let's not do 999, let's just do 500 of the most uncertain records, my accuracy score becomes 0.97, which is pretty good. And in fact, it kind of says that compared to randomness, I only needed half the number of records, okay, to achieve the same accuracy score. So at this point, I'm going to jump back into my presentation. So the question is, and this is the question of the paper, and gee, I just looked at the time, I'm running late. Can we use other information to assess a better score? Okay, so one idea, in my case, suppose that the fraction of records that battery appears in the entire data set is significantly higher than appears in the training data, okay? Well, then that says that maybe battery is an important word, that maybe we should consider using records that in the test data, that we should manually label some records that have the word battery. One way of implementing this might be to find the distance, let's say, between an unlabeled record and the training records. And then maybe if I find a distance, if I find an unlabeled record that is far away from the already trained records, maybe that is another good score to be using to help me assess whether that unlabeled record should be used. So here I just use an L infinity norm, which is going to be the maximum of by word, the my unlabeled record, word J, against the ith record, of my the jth word of my ith record, and then to see and then to minimize over all my records in my training set. The idea behind the paper is to then develop another model, another standard machine learning model that estimates the improvement of accuracy that I would get from an unlabeled record based upon not just one, but maybe 2 or 3 or maybe even 10 different attributes. So the uncertainty score and maybe the distance between it and the already trained data. It turns out that when I actually looked at this particular score, and I went and said, for each untrained, for unlabeled record, can I calculate what my uncertainty score is, and can I calculate what my distance is? And then I went and I said, if I added just that one single record to my training data set, did it improve accuracy or not? And if so, how much did it improve? I could create a data set like this, where some records improve and some records don't. It turns out that in this particular case, adding the distance metric gave me a very low, so a very awful p-value. So it's probably not the best one, but for purposes of the presentation, we're going to keep with it. So the basic algorithm in the paper, and I'm going to use actual numbers here of records, but the paper didn't actually specify 2,000 records or 1,500 records. I just want to make this more concrete. is to take a classifier. Let's begin with having 2,000 records labeled, and we're going to call, and we're going to train a classifier on that and call that model 1. Then we're going to take these 2,000 records and split them up into another training set, a training star set, and a test set. Let's say 1,500 records on this training star set and 500 records on that. Then I'm going to train the classifier again, but on the training star set. And I'm going to record the accuracy of that when I tested that on the 500 records in the test star. Remember that these 500 records in the test do have labels. And we're going and we'll call this model 2. And for each record in my test star, using model 2, I'm going to compute the uncertainty score and the distance score. Then I'm going to temporarily add each record in the test set, in the test star set to the training star set, rerun the training of the classifier, measure its accuracy, and I'm going to come up with a table or a list that says for each record in the test star set, what was the uncertainty score, the distance, and the accuracy improvement. So at the end, I've got 500 records that have these 3 attributes. We're then going to build a separate machine learning algorithm. It could be a regression or a random forest regressor or a boosted tree regressor of some sort to predict the accuracy improvement based upon just the uncertainty score and the distance. What's important to understand is that I can get uncertainty scores and distances based upon a trained model without knowing what the label is. So now I go through all the other 52,000 records that are unlabeled. I'm going to use my model 1, which was trained on all 2,000 records, and I'm going to develop an uncertainty score and a distance score for all 52,000 records. I'll plug these 2 numbers into the regression function that is used to predict the accuracy improvement. And then finally, I can take records with the highest predicted accuracy improvement, let's say the next 1,000 records, the highest predicted accuracy improvement, and manually label them. That's my active learning algorithm. I'm running out of time, but I'm getting kind of close. In fact, we could run this basic algorithm many times because we could split up the original 2,000 record training set into many different train star and test star sets. And we can vary the size of these train star and test star sets. So what that means is that I could have not just 500 records in my regression problem, but thousands. Furthermore, we can use different metrics. We talked about uncertainty. Uncertainty scores and distance scores, but we could also create other scores. Some of them could be based upon not the individual test record, but the actual, but all the records that were used for an individual training set. So if I split up the original training set into several train star, test star sets, I could also develop metrics on that. In the paper, the authors also used a random forest classifier, and they also used other attributes or statistics like the average probabilities and the standard error of the probabilities. They look at the average depth of the trees, fraction of positive accuracy improvements, the added bag score, and so on. And it's proven to be a computational nightmare for me to apply this onto my text classification data set, but I will show you, this is my last slide, results on a green a data set on the corpus Meketon data set, in which they were trying to improve the IOU metric. And the top two lines here are different variations of the algorithm that I just said. The green line is using only the uncertainty score, and then the red line here represents it as the improvement in the accuracy score here, just using random elements. And this is plotting the training size as you keep adding records on by an active learning approach to the labeled records versus the accuracy here. I'm sorry, Sam, I am kind of close to out of time. Any final questions?
Did you, you mentioned that you found this to be computationally challenging to apply to your data. Did you go any further in your notebook with this?
Yes, I did, but I'm like out of time, and the issue is that I was trying to use various distance metrics, and it took hours and hours of time to compute these distances between the unlabeled records and my training data. And my poor laptop was beginning to actually smoke. Well, I'm exaggerating. But it's a good technique, and I encourage others to try it out.
Awesome. Any questions for Mark?
No, just an observation. I think it's a very important area of research, because people usually talk of big data, but this technique tries to reduce the costs of labeling, which I think it's a very good area of research in the future.
Other questions for Mark?
Well, thank you, Sam, and thank you, folks. I'm going to stop share.
Yep, Mark, thanks so much for the presentation. I enjoyed it.
You had some wrap up at the end?
No, wrap up is usually catch us next time. We've got the EMEA meetup in a couple of weeks. And that one is, again, Sharon Glander talking about explainability, and she'll be talking about the Lime paper, which is Carlos Gestrin out of University of Washington, a pretty well-known kind of explainability model. So that one should be interesting, and it's not too late to join the various study groups for the Fast AI courses. But other than that, thanks everyone for joining, and see you next time.
Thanks, Mark. Thanks, Sam.
Thanks, Mark.
Yeah, thanks a lot, Mark.
Bye.
Night.
Sam, are you going to post this video?
Yep, it'll be posted.
My internet cut out there for a while. Okay,
Yeah,
thanks.
it'll be posted, Doug.
All right. Take
Night.
care. Good night.